Release in the seminar series today. Today we have Mike Pavolonis, who's a physical scientist at NOAA Center for Satellite Applications and Research, and NOAA and is an honorary research fellow at NOAA Cooperative Institute for Meteorological Satellite Studies here in Madison. He leads research group focused on studying volcanic clouds, severe weather, and other related cloud topics. He earned his PhD here in the AOS department from Madison, where he was stationed as part of NOAA's effort to facilitate collaboration between government and university scientists. He holds a BS in meteorology from Penn State and his MS also from UW-Madison. Dr. Pavolonis is an active member of WMO expert panels on volcanic clouds and nowcasting, and has authored/co-authored over 40 peer-reviewed journal articles. He's been awarded the NOAA Bronze Medal for the NOAA David Johnson Award and the American Astronautical Society's Earth Science and Applications Award for his work on volcanic clouds and severe weather. So that will take it over.
Thank you, Zoe. It's great to come back up here and be part of the AOS community, as well as our extended family in CIMSS and SSCC. I've come to realize I've actually been in this building in one capacity or another for the last 18 years. So I'm approaching, another couple of years, I will have spent half my life here. And so that's, I must really like it. And so it may seem like these are really two very different topics, and in many ways they are, volcanic eruptions and severe weather prediction. But in some key ways they are related. They both involve rapidly developing clouds, and the development of those clouds, the quantitative characterization of that development is key for both applications, for both practical decision making, as well as just sort of better understanding of these phenomena. So with that, hopefully you'll see the connection as we go. So before, I'll talk about volcanic eruptions and then severe weather, but before I do that, I just want to say a word about data and sort of the era that we're in right now. So data, of course, satellite is sort of the big component that is driving large data volumes, but there are other sources of data, of course. But we've recently, in NOAA, launched the GOES-R series of satellites, or started to launch this series of satellites with the GOES-R satellite and the GOES-S satellite, which are now GOES-16 and GOES-17 respectively, because they successfully achieved orbit. These were preceded by the Himawari-8 satellite launched by the Japanese meteorological agencies. But these are huge upgrades in capability as well as data volume. And there's more of these types of upgrades coming in the next several years. So just for instance, with the GOES-R series, everything's better. You get more spectral channels, so 3 times more specifically. You get 4 times better spatial resolution, and you scan the Earth much faster, so you take much more frequent images. In addition, on the GOES-R series, we have the first time in geostationary orbit a lightning detection sensor. I'll say more about later. So just to give an idea of the type of coverage you get and the frequency in which you get that coverage. So currently, every 15 minutes, you get a full disk. That's going to change to every 10 minutes sometime in the near future. And then every 5 minutes, you cover the continental United States, or an area equivalent to that. And then every minute, you can cover 2 domains about this size right here, or you could cover one of these domains every 30 seconds. And so now, we're seeing with unprecedented detail the evolution of weather. And for phenomena that evolve very, very rapidly in time, this is really critical. Of course, it's not just NOAA that has satellites, but it's a variety of other agencies as well. And so, particularly in low Earth orbit, things are actually getting fairly crowded when you factor in all the space junk. But there's a great number of sensors in low Earth orbit. In geostationary orbit, we're starting to really expand those capabilities. And so when you look at this holistically, there's a lot here and there's a lot of information here, but it's hard to get at because the data volumes are a bit intimidating. So just for comparison, if you look at the geostationary satellite constellation, the legacy constellation, the number of Earth observations each day is this blue bar. With the new generation of geostationary satellites, when you take it as a constellation, it's this red bar. So we're now over 1 trillion Earth observations every day just from geostationary satellites, and that's going to go up further. And of course, satellites aren't the only game in town. There's a variety of other data sources, from numerical weather prediction models, which are getting to be higher resolution. We have radar, ground-based systems. We have lightning detection. All of these are sources of information that are critical for understanding and predicting weather. So it really is a challenge to transform all these data sources into information, not only for decision making, but it also, you can extend knowledge while doing that. So these aren't mutually exclusive. So sort of the blending of the physical sciences with data sciences here. Data science alone, throwing a bunch of data at a sophisticated software system isn't going to get the job done. You have to have an understanding of the underlying physical relationships that the data describes. But when you blend those two together, physical and data sciences, that's where the power really lies. So, in the two applications I'm talking about today, so it would be taking all these data sources, automatically identifying volcanic eruptions, characterizing them, not only for operational decision making, but for better understanding the phenomena. Same thing with the evolution of thunderstorms, improving short-term prediction of those and just understanding them better over time. Okay, so volcanic eruption detection. This is work I do with Justin Siegliff and John Centennial and an expanding group of folks. The motivation. Volcanic eruptions do have a major impact on the Earth atmosphere system. They're more common than you think. The big ones are the ones you tend to hear about, but these happen every single day, multiple times somewhere. And of course, explosive volcanic eruptions have the biggest impacts. You can change surface properties, you can change the properties of the ocean, you can modify weather locally. And of course, the really large ones that inject large amounts of sulfur dioxide into the stratosphere can impact climate over the course of months or years. We haven't had one of these since 1991, Pinatubo. So just a little aside, geologically speaking, we're starting to get to the point where you're wondering, when is one of these going to happen again? And we were in a very different world in 1991. Our ability to observe those eruptions was very, very different. There was no social media. The debate about climate was ongoing, but not the same as it is today. So when one of these does happen, well, the good positive, we'll be able to observe it much better. But on the sort of challenges end of the spectrum, the discussions separating the signal from the noise is going to be a challenge in communicating. And also, you think about weather prediction. In 1991, our 5-day forecasts weren't nearly as useful and good as they are now. And so if you inject a large amount of sulfate aerosol into the stratosphere and the weather models aren't prepared to handle this new forcing, what we've gotten used to in terms of highly skilled weather forecasts several days out may be modified if we're not accounting for this. So this is a big deal. There are, of course, direct impacts on infrastructure and human health, but it's a huge impact on aviation. And that's largely been my focus, but if you're sort of addressing the aviation aspect of this problem, the things that you're doing to address that feed back into all these other aspects. So from an aviation perspective, ash is a major hazard. It's very abrasive. It sandblasts the cockpit windscreen, can actually render it opaque. I've seen a windscreen that's gone through an ash cloud. Airframes and flight surfaces also get scratched up. It can clog the pitot system, so that's a problem. You may not get an accurate airspeed reading then, and of course if you react to that incorrectly, something very bad can happen. It gets ingested into the air conditioning and cooling systems. So it could contaminate the electronics, the avionics, the fuel and hydraulic systems, set off the cargo hold smoke detection systems, make you think something else is wrong with the aircraft. And then most severely, it can damage jet turbine engines. So when ash is ingested in a jet turbine engine, it melts inside the combustion chamber, then cools inside the turbine and deposits on the turbine vanes. And if that happens, if enough of that happens, you can actually severely restrict the flow of the high pressure gases and cause in-flight engine failure. And that's actually happened a couple of times. The first time this happened was on the British Airways flight in 1992, where a flight from Perth, Australia to Jakarta, Indonesia, flew through a freshly erupted ash cloud from Galunggung volcano. And at 37,000 feet, they lost power to all 4 engines and didn't know why. And the captain, Eric Moody, who is not only a very accomplished pilot, but is quite the character, addressed the passengers with, ladies and gentlemen, this is your captain speaking. We have a small problem. All 4 engines have stopped. And then he continued, we're doing our damnedest to get them started. I trust you're not in too much distress. And so this happened at 37,000 feet. So the crew skillfully glided the plane down at a very, very slow rate to about 12,000 feet, where they were able to restart a couple of the engines and then eventually get all 4 engines restarted. By descending, they got out of the ash cloud, and they got out of the ash cloud long enough for the ash to cool and become more brittle and actually break off to a large enough degree that they can get the engines fired again. They had many unsuccessful attempts to restart the engines prior to that, so it was quite the harrowing experience. They were able to land safely in Jakarta. But if you're more interested, search on YouTube. There's a great documentary on it that's about an hour, and they have actually a pretty good reenactment of it. This happened again in 1989, just outside of Anchorage, with a KLM flight. And this is sort of a graphical, computer-generated depiction of what happened. You can see they got in the ash cloud, had a problem, and they were disturbed by, weren't sure the pilot wasn't sure what was going on. They didn't like it, so the pilot decided to try to ascend out of it, climb out of it. By doing that, you increase thrust, you increase the temperature of the combustion chamber, and you actually cause more problems. And they ended up stalling all 4 engines. Except this wasn't over open ocean, this was over mountainous terrain, so less recovery time. But fortunately, they did descend out of it and were able to restart 2 of the engines at about 17,000 feet and made a emergency landing in Anchorage. They were supposed to be going to Narita in Tokyo. I saw the windscreen from this plane, and it was completely opaque. So landing in Anchorage is already kind of a challenge, but doing it under those conditions is a big challenge. This plane is still in service today, but I think it's mainly used by the shipping industry now than it carries passengers anymore. So the economic impacts are also very large. You may remember in 2010 there was a hard to pronounce Icelandic volcano that erupted, Eyjafjallajökull. There's nobody here from Iceland, so that is the correct pronunciation. And that resulted in over 100,000 canceled flights. That's like 50% of the world's air traffic. So airlines were losing 200 million a day. Total losses were in the billions. And so this was, there were airlines that nearly went bankrupt because of this. So this was a very big deal, and it can happen again. Some of it was due to policy. Some of it was due to the properties of the ash cloud and the persistence of it in the atmosphere. But this is a snapshot of what traffic normally looks like. Air traffic over Europe. This is what it looked like during the peak of the event. And so, this isn't. It's not a rare event. There's at least 10 events per year that have a fairly high impact on aviation. And in some places, there are localized impacts much more frequently than that. You can see, with the global reach of jet aircraft, and the red spots are volcanic, major volcanic arcs. Even very, very isolated volcanoes, remote volcanoes, can have an impact on aviation because it doesn't take long for the cloud to disperse thousands of kilometers downwind. And so because of this, there are 9 volcanic ash advisory centers set up all over the world. NOAA operates 2 of them, one in Washington, D.C., one in Anchorage. But they're staffed 24/7 to issue alerts whenever volcanic ash is in the air. There are 1,549 known volcanic events in the world, and only about 10 of those volcanoes are routinely monitored from the ground with geophysical data monitoring capabilities. Most are really, really difficult to monitor because they're either remote or there are other circumstances that make it difficult. For instance, people like to steal seismometers for whatever reason in certain parts of the world. And so remote sensing is really often the only means of detecting explosive volcanic eruptions. So with regards to remote sensing, there are 3 first-order questions. One, of course, you want to know, did a volcanic eruption occur? Did a cloud-producing volcanic eruption occur? What are the attributes and associated uncertainty of those attributes of the eruptive cloud? And then you want to know where it's going to be in the future. So there's a forecasting aspect to this. If you want to know where it's going to be in the future, you have to have an idea what the current state is. And so broadly speaking, there are 3 classes of volcanic clouds as I think of the problem anyway. No 2 clouds are the same. They're very, very complicated, but you can generally classify a volcanic cloud into 1 of 3 categories. The first one is ash-dominated plumes. So these are clouds, at least on the particle end of things, that are primarily composed of volcanic ash. Sometimes they're electrified, sometimes they're not. Sometimes they contain large amounts of sulfur dioxide gas, sometimes they don't. The second class are these umbrella clouds here. These are produced by highly explosive activity. They're mostly the result of major eruptions, and they tend to be very opaque. They're composed of volcanic ash, but they can be far more complex than that. The ash can be encased in ice particles. Hydrometeors are very, very common in these clouds. So a blend of hydrometeors and ash. They also often contain large amounts of sulfur dioxide. These are the clouds that get into the upper troposphere, lower stratosphere after big explosions. And then you get clouds that have very little ash in them and are mainly composed of sulfur dioxide gas and other volcanic gases. But the ones that I'm going to focus on here today are the umbrella clouds. These are the most interesting from a variety of reasons. They have the greatest impacts. They're most hazardous. These are the clouds that if you fly an aircraft through them, you're going to have a major problem. These are also the clouds that if you're going to have an impact on climate, it's going to be from the type of eruption that generates this type of cloud. And these are also, from a remote sensing perspective, particularly from satellite, some of the most challenging to detect. Because unlike the ash-dominated clouds where you can exploit how radiation attenuates differently as a function of wavelength to differentiate ash-dominated clouds from other cloud types, for these umbrella clouds you can't really do that because they're so opaque, and they tend to be composed of not just volcanic ash but hydrometeors, which makes trying to extract a unique multispectral signature more challenging. And so these clouds just illustrate that they are a challenge to detect. I'll point to a particular event in 2011. So there was this volcano in Eritrea here in Western Africa, or Eastern Africa, called Nabro, that erupted for the first time in recorded history on June 12th of 2011. And the eruption went undetected for 7.5 hours. So this injected material up into the lower stratosphere. It's highly explosive, had a lot of volcanic ash, had what would have been deadly amounts of sulfur dioxide had any human been exposed to it. We learned that after the fact. But here's the infrared satellite image that sort of illustrates why this is so hard. These clouds are hard to identify. Well, you have a lot of meteorological convection in this scene. This is just an infrared image. And the eruptive cloud is right there. But if you're just sort of taking a gander at satellite imagery, you think, okay, yeah, there's thunderstorms. Just from looking at this with your eyes, it's hard to know without knowing that is an actual eruption, that without any other piece of information, that actually is an eruption. This was, the Obama administration had an incredible knack for having issues with volcanic clouds between 2010 and 2011. And this was one of them. So this, actually Secretary of State, then Secretary of State Clinton, was in Eritrea when this happened. And nobody knew about this for 7.5 hours. So, you know, you think about the potential to have incidents with major hazards. This one came a little closer than you would like. So, how can we detect this type of eruption? Well, the thing that we've really focused in on is there something special about how the cloud evolves in time relative to other cloud types. And so if you just take an infrared image, here, so this is just a brightness temperature image at 11 microns about. Here's the, an image with the nabro cloud when it's in its emergent phase. And you can see it's characterized by low brightness temperatures because it's growing vertically. And so what we do is we try to identify clouds that are growing vertically in a highly anomalous manner. And so I'll walk you through kind of how we do that. So first thing we do is we take that 11 micron measurement, we transform it into another data space to help simplify the problem. So we transform it into a radiative parameter that scales between 0 and 1. 1 meaning that if you assume the cloud is opaque, it's at the tropopause. If it was 0.5, that means it's kind of in the middle troposphere. 0 means ideally you don't have a cloud there at all. It just makes the problem simpler because what we have to do is identify cloud objects automatically. So by a cloud object, I mean you want to identify a cloud element characterized by a maximum in this parameter, and then you want to track those in time because you need to distinguish between vertical growth and advection. So you need to actually identify and track clouds automatically in time. And so this is just an illustration of that. So if we look at, pay attention to this cloud element here labeled 4, the black outlines are the automatically determined cloud objects. So as you go between 2 successive image times from a geostationary satellite, spaced 15 minutes apart, we have a tracking algorithm that automatically associates the feature in the first image with the feature in the second image. That then allows you to compute the change in the minimum brightness temperature in a cloud between the two. And it is the change in that minimum brightness temperature that is used to characterize vertical growth. But this is more complicated than that. So we can do the vertical growth calculation. So in this case, between these two images, the minimum brightness temperature in the eruptive cloud in a 15-minute time span decreased by about 45 degrees Celsius in a 15-minute time span. That seems like a lot, but is it? We have to figure that out because our ability to observe that vertical growth is not just a function of the change in the minimum brightness temperature, it's a function of other things like the spatial resolution of the satellite. How well do you observe the convective cores? That's determined by the spatial resolution. It's determined by the time spacing between 2 successive images. That the closer the images are spaced in time, the more you can constrain the growth between a certain time interval. And it depends the background from which the cloud emerges. If it's a very messy background with a lot of background cloud cover, the amount of vertical growth that you can observe from a space-based perspective is more limited. So all these factors are taken into account. We build up a very, very large database of meteorological clouds. So no major volcanic eruptions in them. And in this database, we have means and standard deviations of growth between 2 successive images, or change in the minimum brightness temperature between 2 successive images. And we have that, those statistics as a function of the satellite spatial resolution, the time between images, and the background conditions. So this is the statistical database that's relevant to the nabro eruption. So you see meteorological clouds. So this is the change in the minimum brightness temperature between 2 successive images. We see that values where nabro exhibited of about -45 are quite rare. They tend to, meteorological convection, even vigorous convection, tends to lie in a change of about 10 to 20 Kelvin in that same time interval. And so we can then characterize how anomalous the vertical growth was, and in this case it was about an 8 standard deviation anomaly. And so that serves as the basis for automatically identifying volcanic eruptions, distinguishing between volcanic eruptions and meteorological convection. So this is just another example. This is Indonesia. And so somewhere in this image is an explosive volcanic eruption. And just looking at this, it'd be very hard to tell where it is. But if I'll zoom in on the area of interest. It was actually an eruption of Saputan right here. And so between 2 successive 10-minute images, this is how the cloud changes in the infrared. And if we zoom in a little bit more and characterize, so the change in the minimum brightness temperature was about 40 Kelvin within a 10-minute window. If you go ahead and characterize that, it equated to about a 10 standard deviation outlier. And because of that, the cloud was automatically detected, an alert was sent to a Volcanic Ash Advisory Center, and then they take action on it. This is just an example of an alert that comes out of this system. So somebody at a Volcanic Ash Advisory Center either gets a text message on their phone or an email, and it has a hyperlink that links to an alert report where you get a web-based information, images, and the metrics associated with it. Just to put this in perspective, how good are we at distinguishing between meteorological and volcanic events? So each day, we do this globally with a fleet of geostationary satellites. We automatically process about 1.5 million different cloud objects, and each day we get about 2 to 3 false alerts globally. On the whole, it's very effective at distinguishing between meteorological and volcanological events. And so, these alerts are very small. They're kilobytes of information. So this is sort of an example of trying to transform terabytes of data to actual information that is more digestible. So this is a very practical aspect, but we also utilize this to build up a sort of research database. And so one of the things that we looked at was an analysis of many eruptions that formed umbrella clouds over the course of years at a variety of volcanoes, tropical, subtropical, mid-latitude, higher latitude volcanoes, different geostationary satellite coverage, etc. And so looking at all these volcanic events that produced umbrella clouds, and if you look at the distribution of the standard deviation anomalies, we see that about 75% of those eruptions ended up with a standard deviation anomaly of 5 or greater. So that's pretty significant. There were only a few that you really couldn't tell the difference between meteorological convection. Another way to look at it is to rank the events by which produced the greatest anomaly. So we just ranked the top 15 events. And so the top one was this event in Indonesia in 2014, Kelut. It produced a cloud that got to 26 kilometers, which is the highest reaching eruption since Pinatubo, we believe. And that was a 40 standard deviation anomaly. That was a real solid Plinian eruption. And then after that, it gets, how these things rank. There is no easy to discern pattern in the type of volcanic activity, whether or not it involves interaction of magma and water. And I think that just owes to the fact that it's not only the properties of the eruption, it's the properties of the atmosphere that determine how these clouds evolve in time. And so, there is a lot of interplay between the atmosphere and the volcanic process that's actually generating these clouds. Another interesting thing to do, we wanted to see how volcanic activity might compare to the most extreme supercell we can find. And so this is from 2011, May of 2011, during that super outbreak. This was the storm that produced an EF5 tornado near El Reno in 2011, not the 2013 event, the 2011 one. It was well observed by satellite, and this event had a maximum growth anomaly of about 11 standard deviations. So this is a really extreme one, but it still pales in comparison to what a major volcanic eruption will do. We also wanted to look at pyroconvection, so convection triggered by fires, as this can produce rather dramatic cloud development. So we looked at this event in Siberia that was well noted for its explosive development, and that only was about a 4 standard deviation anomaly. Another way to look at these umbrella clouds is through electrification. So we not only have ground-based ways to assess cloud electrification, but on the GOES-R series of satellites, we have an optical sensor that is able to map lightning by sensing the light that makes it out to space. And so this is on the Geostationary lightning mapper on the GOES-R series. So it just gives you an idea of kind of what this looks like. So as far as we know, the GLM has only observed one volcanic lightning event, and that was this past June, when there was a major eruption of the Fuego volcano in Guatemala. It was an eruption generated a lot of pyroclastic flows that were very deadly, generated a tall umbrella cloud. It was a very bad event. And so this is a visible satellite image. I'll play it a few times. And so the circle here is centered on Fuego. The red triangle is the volcano. The yellow boxes are lightning strikes observed by the geostationary lightning mapper. I'll play it again. One thing you'll notice is that the eruptive cloud, the umbrella cloud in the visible, is far more absorbing than the meteorological clouds. That's expected for ash-rich clouds. And you'll note there are a couple of events here. Here's another one right there. And there's varying amounts of lightning that were observed association with the volcanic activity. There was a lot of ambient lightning as well associated with meteorological convection. So we thought it would be interesting to look at how the observed volcanic lightning compared to the surrounding meteorological lightning. I'm not going to dwell into details here, but this is a time series of lightning from the eruptive event, and this is from nearby meteorological convection. The line I want you to pay attention to is the green line, because I think that's the most interesting parameter here. This is the total optical energy associated with the lightning. And these green scales are exactly the same. So one thing you see is that the volcanic lightning is much lower in optical energy than the meteorological lightning. And so one of the reasons that this would be the case is that the volcanic lightning is originating from closer to the ground. And so that more of the light is being attenuated before it gets out to space. Whereas meteorological convection, there's a lot of lightning near the cloud top, and more of those photons are captured from a space-based perspective. And this actually jives well with previous work and studies on volcanic lightning. So this is just an example from the 2014 Kalud eruption. There were a lot of photographs of the volcanic lightning in that particular eruption, and there were also very high frequency-based measurements of lightning, and most of it was observed. The most intense lightning was near the ground, where you're closer to the eruptive vent. That's where the acceleration is greatest, vertical acceleration is greatest, and that's where the concentration of particles is greatest. So the combination of high concentration of particles and vertical accelerations that accentuates the charge separation that you need to generate lightning, and so that's why volcanic lightning tends to be more or less located closer to the ground and the volcanic vent. So those GLM observations were consistent with that, which is nice to see. Another thing we could do after initial detection of these umbrella clouds is track them in time automatically. So if you can track them in time, this is the Kalud event, again, the very large Kalud event. So the polygon around this feature here in the satellite image sequence represents the bounds of the automatically detected cloud. And so if you're automatically detecting and tracking it, you can make time series like this of like the total area of the cloud over time. And it turns out that the radial expansion of the cloud over time is very much driven by the properties of the eruption itself. So what's interesting with these clouds is that the umbrella region, the lateral extension of it over time of the umbrella region is largely, can be described as a gravity current to a first order. And if you look at the right kind of satellite imagery, you clearly see evidence of that. You can see the evidence of gravity waves. And so as such, there are these scaling relationships that allow you to relate the change in the radius of the cloud over time to the mass eruption rate. So how much material is coming out of the volcanic event as a function of time. And you can actually characterize the mass eruption rate over time. And so this has been done for this event. So this is in a new article that will be coming out. So this is for the Kalut event, so which began around 16 UTC on the 14th of February. And so what you're looking at here in the solid line is the lightning strokes per minute from a ground-based network. And then these bars represent the expected range or the range of uncertainty of the mass eruption rate determined from the aerial expansion of the umbrella cloud, which we got from satellite. And that's relative to this axis here. So what you can see is that when the mass eruption rate is changing rapidly with time, that's when the lightning ramps up. So in other words, that's when the acceleration out of the event out of the volcanic event is actually greatest. And then as the mass eruption rate starts to level off, the lightning decreases. And then based off of some other geophysical data and photographs, we know that later in the eruption, as the mass eruption rate leveled off, in other words, the umbrella cloud wasn't expanding at such a large rate, the eruptive column became unstable and started generating pyroclastic density flows at the surface. So it started collapsing. And so by bringing these different data sources together, you can piece all this information about the actual evolution of the eruption. And you can do a lot more. This is just a sampling of that. So this is not only sort of something for practical decision making, but also, you know, there's a lot of room for study of volcanic cloud generation and evolution. So hopefully convinced you, this is not the way you want to detect these clouds from your window seat on your way to vacation. It was actually Soufriere Hills in the Caribbean, and it was first detected by a hairdresser sitting in 15 F. And so with that, we'll try to make a smooth transition to meteorological convection. You can see the similarities. And severe weather forecasting. So this also involves characterizing the time evolution of clouds. And so I want to talk about something called ProbSevere. This is an empirical model that we developed where the goal is to improve the primary goal is to improve the lead time and the timeliness of severe weather forecasts. So by severe weather, I mean the official National Weather Service definition. So 58 mile per hour winds or greater, 1 inch hail or greater, tornado. And so acknowledge John Centineo, Justin Siegeloff, and other colleagues. And we actually had UW-AOS students contribute to this quite a bit over the years, undergraduate students. Okay, so ProbSevere, let's click on all these. So it's a statistical model that blends data from a variety of sources. So what we do is we take high-resolution NWP data, which gives us information on the dynamic and thermodynamic environment. We combine that with cloud evolution that can be quantitatively inferred from geostationary satellites, just like I showed for the volcanic eruption detection. That gives you unique insight into the evolution of the cloud from the cumulus stage to convective initiation to a mature cumulonimbus. And then we have, of course, NEXRAD. So when a storm, after convective initiation is achieved, of course, you're going to be looking at radar that's going to provide the most detailed insights. And so that's a key component here. And then we also have measurements of lightning from both now space and ground-based sensors. All of this goes into a naive Bayesian classifier to determine the probability that a developing thunderstorm will produce severe weather up to 90 minutes in the future. So it's a prognostic tool, not a diagnostic tool. And it actually is operating on existing convection that you can see in some observational source, satellite radar. So it's not forecasting where convection will be. It's actually characterizing existing convection. Not going to go through all of this, but in addition to trying to determine the overall probability of severe of a developing thunderstorm, we do it individually by the probability of severe hail, probability of wind, and the probability of tornado. And it's really three separate statistical models for doing this. And they have different predictors. These predictors weren't sort of just chosen out of thin air. There was a lot of time thinking about the physics and what's relevant to the problem. I've yet to see a statistical model in atmospheric science where somebody with no knowledge of the problem threw a lot of data at a computer and it solved a bunch of problems for them. So you do have to have an idea of what the underlying data is telling you. So this is just how we display this information. So during when thunderstorms are evolving, of course you're going to be looking at radar. You're not going to be looking at satellites so much. You're going to be looking at radar. So this is just NEXRAD radar reflectivity, and the probability of severe is displayed as contours around individual storm cells that are determined automatically by a feature identification and tracking algorithm, just like I described for the volcanic eruption detection. And so as the colors go from purples to blues to magenta, the probability gets higher. And then you can mouse over and you can actually get a listing of all of the metrics that went into determining the probability. So you get an idea of maybe why the probabilities are evolving in time the way they are. The nice thing about very simple machine learning is that there is this intuitive connection between how the probabilities evolve and how the metrics that go into determining the probabilities evolve. With more sophisticated deep learning, that often you lose that. So just an example of how this works and what the value of it is, at least for operational decision making. Just take sort of a typical event here with a marginal probability of severe from the Storm Prediction Center here in southeast Texas. So this is showing the results of the probability of hail. And so we're starting off here, this is on March 5th, 2018. We're starting off at 2236 UTC when the probability of hail at this stage as the thunderstorm is just forming is only 3%. We march ahead 2 minutes. This updates every time a new piece of information comes in, every time a new radar observation, every time a new satellite, every time new lightning information or NWP comes in, we update the model. We get a new set of probabilities. So 2 minutes later, we have new information. The probabilities update to about 11%. And then if I jump ahead here, we're now at 29%. There's no severe thunderstorm warning on this yet. It doesn't look all that bad in radar yet. And then in this 2 minute time period, between 2252 and 2254, probability jumps up to 63% that this storm will produce severe hail some point in the future. And then if I jump ahead even further, the probability jumps up to 92%. And then 2 minutes after the probability went to 92%, that's when the National Weather Service issued a severe thunderstorm warning. Actually, it was not 2 minutes, it was 8 minutes. I fast forwarded 8 minutes there, yeah.
What are the dominant variables that are triggering that here?
So, it depends on the stage. So early on, so at this stage, probability jumps from 11 to 29% largely because of the evolution in the satellite. And then as you go on here, it's the integrated reflectivity of the radar. So the maximum expected size of hail is an integrated metric derived from reflectivity. That begins to increase And then lightning also increases while the integrated reflectivity increases. So it's all these pieces of information together. And this would be something that's very hard for a person to do on the fly when you're trying to look at a variety of storms, integrate manually all of these pieces of information.
Well, once you see that white in there, you know there's already large hail in there. I've never seen white in reflectivity that did not produce large hail. That's like 70 dBz.
At this stage, there were no observations of large hail. The first report of large hail came, I think, 18 minutes after this. Let's see. So yeah, okay, this is 2302. So yeah, it wasn't until 10 minutes after this that a severe thunderstorm warning was actually issued. And then,
And yet I'd be willing to bet if there's white in there that there's somebody that's just not reporting it, but that's got to be large hail if it's that big.
well, it's also the color scale. I'm not sure.
Yeah,
if it
maybe a
corresponds
different
to the
scale than
same.
I'm used to. Yeah.
Yeah.
Okay.
Yeah. And then it was 8 minutes after the National Weather Service issued the severe thunderstorm warning that actually did get confirmation of hail. So you see the idea here is that you get confidence that a storm is going to produce severe weather ahead of just if you're relying on manual interrogation of radar alone, because it's integrating these various data sources. Just one more example. This is from the tornado, EF3 tornado in May of 2017 in northern Wisconsin. It was the longest track tornado in Wisconsin, I think, since records started in 1950. Did quite a bit of damage. And so now we're looking at the probability of tornado. So this is the storm of interest. So we have the probability highlighted over time here. And so I'll just sort of watch this play. So this is probability of tornado now. And so you see the probability ramp up steadily over time. And then here's when, that's the point when the tornado actually touched down, and you see it evolve, and I sort of just fast forward there. But another way to look at this is in time series form. So we auto-generate these time series as well. So what you see in red here is the probability of tornado, blue is the probability of severe wind, and green is the probability of hail. It's a function of time for the same storm, northern Wisconsin. Where you have yellow bars stretching here, that is the duration of a National Weather Service severe thunderstorm warning. Where it's red, that's the duration of a National Weather Service tornado warning. The vertical green is where we have reports of severe hail, and then the tornado reports are in magenta. And so what you can see is that prior to a tornado warning being issued, the probability of tornado really starts to ramp up, especially relative to neighboring storms. That storm really stood out. Prior to any severe weather warning being issued and any severe weather being reported, the probability of both hail and straight line winds was very, very high. And then the probabilities remain high. They fluctuate a bit, but remain high prior to the touchdown of the tornado. Another way to look at this is really busy, but you can look at it as a function of all of the various predictors as well. So there's not a lot of detail I want to go into here, but the orange lines are representative of the azimuthal shear variables that we're using from the radar. And so you see that the probability of tornado, to a large extent, evolves as those variables evolve. But it's not quite that simple. There are plenty of cases where we get large spikes in lightning that will actually jump the tornado probability. So it's not just tracking something that you can simply see in radar alone. It's a little more complicated than that. There's a lot of verification done on this. And so if you're doing probabilistic, you want to know how well calibrated your probabilities are. So this is a reliability diagram. So this is for overall probability of severe. So how well does your probability match the actual frequency of occurrence? Perfect would be along the blue line. But you can see that it is skillful over a broad range of probabilities. Do tend to over-forecast relative to local storm reports, which have their own issues at the higher probability ranges, but overall pretty well calibrated. And so here's the main point, the value of this. So if you compare how the model does to National Weather Service forecasters, The orange bar is the model, ProbSevere, NWS is the blue bar. So in terms of skill, the human is still better. We kind of expect that. We weren't expecting to beat them on skill. But if you look at the median lead time to the first report of severe weather, the model adds 18 minutes of lead time compared to the human. That's where the value really lies. We did this for probability of tornado as well. We see we're still pretty well calibrated. For tornado, the lead time is increased by 11 minutes compared to National Weather Service warnings. This is a bit more complicated, but it's very promising. Just one other thing, I do want to point out the satellite does play a role here, especially in the lead time. So the green bar is the lead time if you remove satellite from the model. The orange bar is if you utilize satellite along with all the other data sources. So you lose about 10 minutes of lead time if you take the satellite part out. We're also starting to use this to sort of to study do long-term analysis of convective activity over the continental United States. And we're confident we can do that because if you look at the number of severe weather reports as a function of month, this is from 2017, so this is the blue line, and compare that to the number of storms with a maximum ProbSevere probability at some point that exceeded each of these values, you see that they're highly correlated. And so this really is a data-rich set that we have here, more than just a report of whether or not a tree fell down. This is now used by National Weather Service forecasters routinely, and yeah, it just shows you, every hour we take in about 10 gigabytes of data, and we make about 6 megabytes of output. So it really does distill that fire hose of data into usable information. We have this in a web mapping service as well, so if you're a chaser and you want a little extra insight, maybe check it out. More information, papers. Okay, so just to wrap up, one quick thought on data science and where we're at on that and the importance of the physical sciences. So this is a figure from IBM. So if you look at traditional machine learning versus deep learning, because deep learning AI, it's a buzz, everybody's talking about it now. There's a reason. Deep learning, if sufficiently trained, if you have a sufficient amount of labeled data, so you see as the amount of data you have increases, you start to get much better skill compared to what you can achieve with traditional machine learning. But this is the catch. Having enough of the right kind of labeled data. That's not easy. So for a lot of meteorological problems, I still feel we're kind of right here on this curve, where we don't have enough data to take true advantage of deep learning. And so I think that'll change over the next several years. As more and more undergraduates get locked in dark rooms to manually classify data, I think we'll start seeing that. And so if you're looking to, this is a good skill to have, I think, looking at deep learning, but not forgetting the physics behind it as well. So yeah, the big main points here is, without auto generation of information, these data sources are going to be underutilized. And I think this is a really good opportunity to improve not only decision making for the benefit of society, but also at the same time extend knowledge. So we can detect volcanic eruptions and keep aviation safer, while at the same time collecting interesting data sets where we can study those clouds. And this is only going to continue to improve. There's more new data sets on the way. And with that, I'll leave you with a quote from a famous pioneer in machine learning. This sort of, the machines aren't going to take over for us, and we can't rely on the machines to solve the problems for us, but they are a very important tool.
So let me get this straight. The difference between deep learning and machine learning is deep learning is where you provide some relationship between the data and the events, that you tell them what it means, or you tell the computer what it means in some sense. Is that what you're saying?
It's more than that. You know, deep learning, when you talk about deep learning, you're talking about things like convolutional neural networks. These things that have many layers and many ways to connect different data sets and find relationships. And in order for it to do that well, there has to be a tremendous amount of labeled data in order to uncover that. Traditional machine learning is things like Bayesian classifiers, linear or logistic regression, and so I think they both rely on providing data to the machine that has physical relationships to exploit. With traditional machine learning, I think you have to be a little bit more thoughtful about the type of data you're using and the physical relationships between those data if you really want to get maximum skill. With deep learning, you still have to have an understanding of the data and what it's telling you, but the learning techniques are better at unscrambling relationships than you are with traditional machine learning. So
You don't know why they do it, right?
but
It's a black box.
it's a black box, and but I've yet to see for atmospheric applications, I've yet to see a deep learning application. There's a lot of papers on it, but I've yet to see a mature deep learning application where that's actually proven over time. There's a lot of prototyping, but I've yet to see something that's proven over time. I think that'll change, but
Is what you're doing deep learning?
no,
It's still machine learning?
it's still classical machine learning. But I think the databases that we're developing will be conducive to deep learning. So over time, we're gathering all this information on storms, and we're doing in a way that has both practical impacts and sort of long-term research impacts. And so I see that transitioning into a more of an artificial intelligence framework. at
So
some point.
deep learning is more equivalent to the brain than
Yeah, it's designed to,
Not mine.
yeah.
because that's the way we learn
Yeah.
in that sense.
Yeah, mimic human learning.
Yeah.
Right?
Yeah, so this is not exactly the focus of what you talked on, but I've always been intrigued by the existence of lightning and volcanic plumes. And I assume that there's some parallels in what happens in volcanic plumes versus what's happened in traditional NESDIS. But a lot of the textbook discussions of storm electrification involve water and ice processes, which are probably not present in plumes. So is anybody actually studying the physics of electrification of volcanic plumes and how it is either similar to or different than what's going on in thunderstorms?
Yeah, it is an ongoing area of study. It's actually a pretty immature area, and so there's a lot of room for study there. So those umbrella clouds generally do have some hydrometeors in them. So there's no doubt that at least some of the time water is certainly playing a role.
But as you say, a lot of the lightning may occur at lower levels where you just have
Right.
dense ash coming out.
Right, out of a hot vent,
Right.
and you're, yeah. There are models that can simulate this now. They're very computationally expensive, but there are column models, and there's a lot of unanswered questions. I don't have any, I can't provide any additional insight into that, other than we know that a lot of it occurs near the vent where the most dynamic part of the eruptive processes are unfolding. John?
Yeah, Mike, it's really interesting. I had one question about the last part when you're dealing with the probability of KLM tornadoes. Is the sequence of the, that map, the chart you showed with all the different lines on it, you said don't worry so much about the details, but
Yeah.
it seems like there might be some information in the thousands of cases you've compiled about the sequencing of when does the tornado risk finally come alive. It's not just one probability number, there's something else underlying it, you're right?
Yeah, absolutely. Another way of looking at it is, so if you have a field, you have a variety of storms in a region. It's not so much what the probability is of a given storm, it's what is the probability relative to the other storms. So is there a storm that stands out? And so the model tends to be very good at picking out the storm that needs the attention, or is most likely to form a tornado. So the maximum probability might only get to 25%. But the probability of every other storm might be 0% or 1%, something very, very small. And so I think that speaks to what you're getting at in terms of it will find relationships in the variables that are more favorable towards tornado formation. But it's an inherently uncertain problem. Predicting tornadoes, right? I mean, we don't have, yeah.
Is your model dedicated to finding that sequencing, or is it dedicated instead to finding probability of occurrence? Because they're not quite exactly the same thing.
They're related.
Yeah, they're related. One will lead to the other, but you might get more process-oriented information if you dedicated it to the sequencing. I suspect. I don't know how you work.
Yeah, there is time information in the model, so it does take into account the evolution. So not just the state at every time a measurement is taken, but actually does take into account the time sequencing. For instance, in lightning, we're looking at trends in lightning, because that is often thought to be related to intensification of updraft.
So you're basically identifying volcanic eruptions by the speed of the cloud vertical growth, right?
Mm-hmm.
And so what causes false alerts?
Generally vigorous, meteorological convection. We also have an algorithm that automatically identifies and tracks clouds. It doesn't do that perfectly. Clouds can be very transient, and in that case, they become very hard to track. So the two things that cause it are genuine overlap with meteorological growth and just bad tracking.
Well, it just seemed like when that one histogram showed the meteorological stuff didn't go very high, so I don't see how they would confuse.
Right. Our alerting, though, is we err on the side, we don't want to miss eruptions, so we'll take on some false alarms to get at early and consistent eruption detection. Jim?
So she asked exactly the same question I was going to ask, which is great. I don't have to ask it, and I get to ask another one. But yeah, it did seem like there was a lot of separation in that histogram, so I was surprised by the false alarms too, but I guess you were showing only extreme case.
Yeah, well, I mean,
You change your threshold, and I guess then you would have more misses, obviously, that's what you're saying.
well, I mean, we process 1.5 million objects per day, so that's 1.5 million opportunities to make a mistake usually. And so,
Right, but when you're talking about 10 standard deviations, I mean,
right.
it's so well.
Oh, yeah.
separated.
You don't get genuine growth that achieves that very often. The only time we get that is through mistaken tracking.
All right. So my other question is, one of the biggest questions right now in climate science, in terms of extremes, is whether extreme severe convective systems are changing over time.
Mhm.
So I'm kind of wondering, how far back does your ProbSevere go, and can you go back and create a longer data set of those?
We currently go back to 2014, although the data sets that we used have evolved a little bit in that time, especially the satellite bit.
So they're heterogeneous.
So that is the challenge.
Can you do historical runs with it and go back in time? Is the data available?
That's possible. We're limited by the radar data set that we're relying on. We rely on the multi-radar, multi-sensor data set, the MRMS, so it blends together all of the NEXRADs in a coherent way and quality controls them. So that only goes back, our archive of it only goes back so far, but in theory it's possible.
It seems like a really useful tool to look at that.
Yeah, I think there's a lot of useful analysis that can be done there, and it would be, I hope someday we get time to explore that.
No, thank you.